Motion on a smooth plane curve. Let us suppose the position of particle on curve at any time, let it be t, be p, whose coordinates are x, y, with arc length s measured from the fixed point p. Let x, y are components of force acting on the particle along coordinate axis, and normal reaction r acts at p on the particle because the curve is smooth. Now, on resolving the forces along the tangents, the motion is given by mv dv by ds equals to x cos psi plus y sin psi, which we suppose as equation 1. But cos psi is equals to dx by ds and sin psi is equals to dy by ds. Then from equation 1 we get mv dv by ds is equals to x dx by ds plus y dy by ds. On integrating this above equation, we get this equation: half mv square equals to integration of x dx plus y dy plus c1, which is a constant, which we now this equation we suppose it as equation 2. Let us take x dx plus y dy as del psi x comma y. Now further taking capital X as del phi by del x and capital Y as del phi by dy, then we have the following equation, which on integrating gives us half mv square equals to phi x comma y plus c1. Let us suppose as equation 3. Here phi x comma y is known as a work function and half mv square gives us the kinetic energy of the particle at point p x comma y. Let initially the particle of mass m starts the motion with velocity v from point p x naught comma y naught. Then the equation 3 gives us half mv naught square equals to phi x naught comma y naught plus c1. Let us suppose this equation as equation 4. From equation 3 and 4 we have half mv square minus v naught square equals to phi x comma y minus phi x naught comma y naught. Let us suppose this equation as equation 5. The RHS of the given above equation shows the work done in moving particle from p naught to p1, whereas the LHS shows the change in kinetic energy of the particle. So, change in the kinetic energy of particle is equal to the work done by the total external forces. The equation 5 is the energy equation, and the force of this type are known as conservative forces. The potential energy of the particle in the position P is equal to the work done by the forces within the position. On integration, we get the following equation where the potential energy comes out as phi x dash comma y dash minus phi x comma y. Let us take this equation as equation 7. But we know that the kinetic energy half mv square equals to phi x comma y plus c1. Now adding equation 8 and 9, we get kinetic energy plus potential energy as phi x dash comma y dash plus c1, which is the constant. Central orbit with application of Kepler's law. Central orbit. A force which always directed towards a fixed point is known as the central force. The fixed point is known as the center of force. The particle described by the particle under the action of central force is known as the central orbit. Kepler's law of motion. First, each planet describes an ellipse having the sun in one of its foci. Second, the radius vector drawn from the sun to the planet describes equal areas and equal time. Third, the square of period of time of various planets are proportional to the cubes of major axis of the orbit. The second law says that the aerial velocity is constant, that is, r square theta is constant. Hence, the force of planet is entirely directed towards the sun. From the first law, it follows that the force on the planet is inversely proportional to the square of its distance from the sun. Application by the Kepler's law. The differential equation of path is given by d square u by d theta square plus u equals to p upon h square u square. Let us take this equation as equation 1, where p is known as the central acceleration. The equation of the ellipse with focus as pole is given by L by r equals to 1 plus e cos theta, which is taken as the equation 2. From this we get u equals to 1 plus e cos theta upon L. Now differentiating this with respect to theta, once we get minus e sin theta upon L, and twice we get d square u upon d theta square as minus e cos theta upon L. Now putting all these values in the equation we get E cos theta by L plus 1 plus E cos theta by L equals to P upon H square U square. From this we get P upon H square U square as 1 upon L, which implies that P is equals to H square U square upon L. Now this can be written as P is equals to mu into U square, that is U mu upon, where mu is equals to H square upon L. From this we can write H as under root mu L. Now it is very clear that P is inversely proportional to R square. Let us take this equation as equation 3. Now we also know that V square is given as H square du by d theta whole square plus U square. Now putting the values, we get mu into L minus E sin theta upon L square plus 1 plus E cos theta upon L ka whole square. Now solving this whole equation, we get V square as mu 2 by R minus 1 upon A, where A is the length of the semi-major axis. This implies that V is less than under root 2U upon mu. Now let T be the time period to complete the arc of ellipse, then half H, the sectorial area described per unit of time, will be half H into T equals to area of ellipse, which is equals to pi AB. Now substituting the value, we get 1 by 2 under root mu L into T as pi AB. Now we get the value of T as 2 pi A to the power 3 by 2 upon under root mu. Now there are further two cases. Hyperbolic orbit, in this case V is given by V square is equals to mu 2 1 plus E cos theta upon L plus E square minus 1 upon L, which is equals to mu 2 by R plus 1 upon A. Hence P is equals to mu upon R square. Now in case of parabolic orbit, here E equals to 1, that is P is equals to mu upon R, and V square is given by 2 mu upon R.